Hey, how you doing?
Hello. Hi.
Hi.
Okay,
How are
there
things
we go.
going?
We have a test this Friday and I've been practicing nonstop.
Yeah.
I think the biggest issue, because we had two checkpoints, checkpoint 1 and 2, is just the comparison. So that's what's going to be taking a while. But I think what I need the most help with is just naming like the R and S type of nomenclature.
Okay.
Because I think I get a lot of it wrong with like the dash, and then also just like being able, not so much the chirality, but it's more of like the 2R, 3S. Like I don't know where the 2 and the 3 comes from exactly.
Okay. Let me ask you this. One of the formats you probably need to know is called the Fischer. Is that correct?
Yeah.
Okay. Are you also responsible for line like this?
Yeah.
Okay. Can you think of anything else that you might be responsible for?
The Newman.
Okay. So R and S in the Newman?
Um, no, wait, not in Newman.
Okay, because
Yeah,
that's very
just
hard.
the bond line.
So I think then you're talking about just these two.
Mm-hmm.
Okay, let's start with this here because this is easier. What we'll do is we'll put a chlorine here. And we'll go ahead and determine what the priorities are. Do you agree that the low priority group is going back?
Yes.
Okay. Do you agree that I am correctly numbering the three groups attached to this carbon?
1, 2, 3. Yeah.
Okay. And do you agree that this is going to be R?
Yes.
Okay. Now tell me if this looks good. What I'm going to do is I'm going to call this 2R chlorobutane. How about that part? So what I'm doing here is I'm going to number this here in the following way. And I'm doing that because it gives the chlorine the lower number.
Okay.
So my longest chain is going to be here. And that's a butane.
All right.
And the chlorine is on carbon number 2. And
Okay.
we've
That makes sense.
determined that the chiral carbon, where the chlorine is, has the R configuration.
Okay.
Okay, so this is the simplest one. One chiral carbon, everything is just very, very clean. Does that make any sense?
Yeah, that makes sense.
Okay. So what we're going to do now is we're going to ask you to tell me what you expect the name for this to be.
So then, since it's dashed, would it just be 2S?
Yes, it will be 2S, chlorobutane. Would you also agree that the hydrogen will be coming out of the plane of the paper here?
Oh, because it's the CL goes back. Okay, yeah.
And for most carbons that are going to be sp3 hybridized, you're going to have a bond here and a bond here that are going to be in plane. In plane means in the plane of the computer screen.
Okay.
That would mean that if you were to touch the computer screen, they wouldn't be sticking out and they wouldn't be going in. They would be right there where you touched. And then because it's a tetrahedron, you would have a bond coming out of the computer screen and another bond going into the computer screen. So
Okay.
this is the way that carbon looks a lot of the time. Not all of the time, but when you're doing these line drawings that we see over here, that's what we're going to see. What that means is if you have a carbon that's chiral and it's a line configuration like this, that you're going to have two lines in plane, one line out, and one line in. And that's useful because it tells you what to do when you're working these problems. Does that work for you, or?
Yeah, it's just like, is it always that the dashed is S, or is that just because of this situation?
It's not. It's not.
Okay.
Right. That's
okay,
not
so there's no really like a trick to it. It's kind of, you just have to do the chirality of,
yes.
Like say you have two of them and then.
Yes. There is no trick to it. You have to do it. I'm only telling you it's this way. So when you get a line drawing, you have everything in the right orientation. You still have to do it.
Okay.
So let's go ahead and do it. You will correct that this is S because when you switch two groups, R and S are going to change. So if I take these two groups here, whatever they are, and I switch them, the R and the S are switching. That's what we did here. You looked at this and you said, you might not have called it switching. You probably want to call it switching. These two groups switched. Therefore, if this is R, this must be S. Now, some people say, oh, the chlorine's out and here it's in, so this must be S. Well, that can backfire. The way to do it is to say, if you know this is R and you switch two groups, then you know this is S. That's the way to do it.
So in this case then, or maybe in every case, the enantiomer basically of it would be the opposite configuration.
Right. If there's only one chiral carbon,
okay,
right, that will be true.
Okay.
But let's say we didn't have this to start with. We didn't have this. Let's say that we were given this structure to begin with. So what we're going to do is we're going to say, oh, that's gone. And now we have this. And what we want to know is what's the name of it. So what we're going to do to name it, hey, I don't know why that won't erase. There we go. Okay. So in order to name this, we're going to take a look at where the low priority group is. Here's the low priority group. So when the low priority group is coming out of the paper, the best way to do this is to go ahead and number it as we did before, and then realize that we're going to have to report the opposite answer. So that means this will be S.
Hmm.
We do it opposite because it's fastest. We do it opposite because the low priority group is coming out. So when you have a situation where you have the low priority group coming out, what you're going to do is you're going to do it opposite. Does that make sense?
So if you did the dashed one, basically, I'm trying to understand why you go back opposite. Like, I understand you switch it, but the priority, like if I were to count the priority of it, it's still
I'm going to tell you
R.
something that works great for orgo and everything else that has to do with logic. But you have to listen carefully because most people don't think this way. If an outcome has only two possibilities, if an outcome has only two possibilities and you do everything correct, you get the right answer. But if you do anything wrong, you get the wrong answer. And there are no other answers. So if you do something wrong, you get the wrong answer. What did we do wrong? We did this wrong. We didn't repair this damage to the system. What damage are we talking about? This is supposed to be going into the plane of the paper. It's not. So instead of fixing it, which is hard, we just do it and we understand that whatever we get must be wrong. And since there's only two choices, we know the right answer. So it's a trick. Does that make sense?
Okay, yeah.
Now, it doesn't really matter if you understand it. It's good if you do. As long as you can do it, recognize that the low priority group is coming out and just go ahead and do it opposite. So we could summarize everything here by saying that if the low priority group, if that low priority group looks like this, then what you do is you just do it. But if that low priority group is like this, then what you do is you do it wrong. Now, it's just as easy to do it right as to do it wrong here. All you're doing is doing the same thing and just reporting the opposite.
Okay.
So the alternatives is horrible because most people don't have the ability to rotate this molecule 180 degrees through the plane of the paper, which is one way, another way of doing this. So this is the simplest way.
Okay, so when the lowest priority group comes out, then it would be S.
Well, it won't be S. It'll be R or S.
Okay, so it'll be the opposite configuration of the.
It'll be the opposite.
Okay.
Now, remember how I said that if you switch two groups, you get the opposite configuration?
Yes.
Okay. So let me ask you something. This is S, correct? We worked this out. This is S.
Yeah.
Okay. So what I'm going to do here is I'm going to go ahead and draw this like this. And I'm going to put the hydrogen over here. And I'll put the chlorine over here. And I'll put the methyl group over here. Now, as far as switching things, the methyl has switched with the hydrogen. Do you agree?
Yeah, because the hydrogen is the lowest priority in this group. So.
Well, it's not because the hydrogen is the lowest priority group. It's because that's what happened. In other words, when I say it was switched, I look at it and I say these two were switched. I'm not saying what's the low priority, high priority. I'm just saying it's it's a lot like having two pens and doing this. They switched. It's not because this is green and this is black. They switched because they are now occupying the other pen's position. Does that make any sense?
So basically, because I have like the model kit, so basically it's like turning, I guess, like this, like it's just turning.
No, it's not. Okay, I'm not trying to get fancy with models here, but I have a feeling that the idea of switching two things in your mind works perfectly when we're not talking about molecules. In other words, I believe that you understand this concept when it doesn't have to do with orgo. Like, what I need for you to do is to use that knowledge here. You're applying too much information to what I'm talking about. Let's say you had a ping pong ball that was white and a ping pong ball that was black. And the ping pong ball that was white was here, and the ping pong ball that was black was here. And you showed them to a kid, and you say, okay, now I do this. And the kid said, you switched the positions of the ping pong ball. You wouldn't say which is low priority or high priority. The concept of switching means that you transpose two things. You could have a lamp in a room, and you could have moved the lamp from the left side of the room to the right-hand side, and someone would say, you switched where the lamp was. When I'm talking about switching, that's all I'm talking about. I'm not talking about organic chemistry. Look, here's the methyl. It's now here. Here's the hydrogen. It's now here. I switched these two. If you wanted in terms of molecular models, I broke the bonds. Because you can't get from here to here using molecular models unless you break the bonds.
So then would that just be like a constitutional isomer, since you're just reconnecting, like taking it apart and reconnecting it into two different spaces?
Okay, but a constitutional isomer is not defined that way. I'm afraid of getting too, like, here's my problem. I don't want to get into all these things. I just want you to agree that they're switched. They're not constitutional isomers, but I don't care. You can't use your model set to move them, but I don't care. All I care about is that you come to my side and tell me, yeah, I got it, they're switched.
Okay, so it doesn't have anything to do with like the concept then.
Well, see, here's the thing. If you need to learn this, you don't need to think. It's great if you could understand this at a deeper level right now. But right now, you need to understand this at a superficial level, and we can work on going to a deeper level later. But if you need to learn how to name these things, this is what you need. That other stuff you're mentioning, I would love to talk about it with you, but you don't need it now. It will just distract us. So let me just do this. Yeah, let's do this. All right. I got it. I need to add another color to make this work very well for me. Okay, so what I'll do is I'll put a purple here. And I'll put a green. Okay. These are not atoms, they're not molecules, they're not ping pong balls. I don't know what they are. We don't care. They're just this now. What I'm going to do is I'm going to change something. And I'm not going to tell you what I'm changing. I'm just going to go like this, and I'll say, like that. Okay, so what happened is I'm going from here to here. I switched the position of two groups. Can you tell me which ones they are?
The purple and the red.
Oh, yeah. Well, that's it. That's how you do it.
Okay.
So let's come over here now. I might not reproduce the same thing. That's okay. Okay, I'm just doing something different. Okay, and then over here, what we'll do is we'll put a CH3. Okay. So this is analogous to this. So analogous means it's pretty much the same exact thing. All right. So do you agree that basically there's 4 different groups here, right? There's 4 different groups around this carbon, right?
Okay.
Now I'll tell you, I switched 2 groups. Okay, and by the way,
did the H and the CH3?
yeah. That's
Okay.
that's what I mean by switched. So this is on paper. We're doing this on paper.
Okay.
So all I'm trying to get at is the concept of switched, not organic chemistry, just the whole idea of switching 2 things and keeping everything else the same. So I am assuming that you agree that these are the groups that have been switched. The ones with the black.
Yeah.
Okay. When on paper you switch 2 groups of a chiral carbon, R and S switch 2.
Okay.
So these are little skills that you can use to make your life easier when you're doing this. So I'm coming over here. I'm going to go 1, and then I'm going to come over here and I'm going to go 2, and I'm going to go 3. I'm going to see the low priority group is coming out. So I'm going to go 1, 2, 3 and turn around, and I'm going to call this S.
Okay.
What's this? S or R?
It'd be R since you're
Yes.
switching.
Yes, that's what I'm getting at.
1, 2, 3. Okay, so 1, 3. Okay. Can you do one that it's R, like starting R and then to S?
I could,
Let's see.
but it's really not where I'm going. Like, I'm afraid to tell you that that's not relevant. I'm showing you that there's a skill here. It doesn't matter if you go from R to S or S to R. It doesn't make any difference. It won't help anything because the point is that when you switch two groups, R and S switch, it doesn't matter what's S, it doesn't matter what's R. What matters is this works. And you can use it in huge ways. You can have a test that has 8 different molecules, and using this skill, you can do one of them and know all of them with this. That's what this is good for. So I know you think about other things. Is it a constitutional isomer? Is it a stereoisomer? Is it like my model set? Why don't we just say that this is a trick? It's a magic trick. And what I want to do is show you how to use it. I mean, I can teach you why this works, but it won't help you on the test.
Okay.
Talk to me about what you're thinking here.
I'm trying to see how this is applicable to the naming specifically,
Okay.
like the 2R and
Let's do something like this. This is pretty much what we have here. Okay. I didn't finish what I wanted to do. And I regret that. I'm going to go ahead and show you something to answer your question. And I hope to come back and finish it, because what I was giving you was a set of tools to determine R and S. And we only got through 2 of them. But this is where I would have gone next. So what I would have done is I would have done this. Okay. So this is sort of along the lines of what we were doing, but it's something else. So this is a chiral carbon here. And so is this, and so is this, and so is this. When there's only one chiral carbon, there are no diastereomers. If there's no cis or trans, if there's no second chiral carbon, there are no diastereomers. Everything is either identical or enantiomers. Does that make any sense? Or?
So if it's only one chiral center, then it can't be a diastereomer because it needs
Right. If there's a chiral center and there's no cis or trans double bonds, then it's going to be identical, or it's going to be enantiomers.
Okay.
Okay.
That makes sense. That makes sense.
So what happens over here is, do you agree that those are mirror images?
Yes, because you just flip it.
Yes. So those are enantiomers, right?
Yeah.
Okay. Do you agree that these are mirror images?
Yes, because you flip it down.
Right. So these are enantiomers as well. How about these on the bottom?
Yes, again, because you just flip it
Right.
that way.
And how about these? These
Yeah, you flip it up. You flip it up.
Okay. So what we're saying here is that the enantiomers are going to be like that. They're going to be like that. They're going to be like that. And they're going to be like that. Do you agree with that?
Mm-hmm.
Okay. Are any of these identical? So there's a hard way to do it, an easy way to do this. I'm hoping for the easy way.
Isn't that if it changes, like all of them change the dash to the wedge, then it'd be an enantiomer. But if not, then they just be identical.
But that dash and the wedge are great, but I'm also moving the carbon skeleton. You know, you can't just say dash and wedge if the carbon skeleton shifts. I don't know if that makes sense, but if you move the carbon skeleton, you're also moving the dash to a wedge and the wedge to a dash. So if you're using wedges and dashes to figure things out, it's not going to work.
Okay, so then none of them would be identical.
I'm not saying none of them. I'm just saying that's not the way to work it. Okay, let me be clear. If you're going to work with dashes and wedges, you're going to also have to work with carbon skeletons. Because if everything stays the same, then you can basically just look at dashes and wedges like we did. But if things are changing, you can't. You have to do more. And it turns out it's hard. So let's take a look at an easy way to do this. Watch. If these are enantiomers and these are enantiomers, these must be identical. They must be. See, the logic is that a molecule can only have one enantiomer. If this is the enantiomer of this, and it's the enantiomer of this, then these must be the same because the molecule can only have one enantiomer. Does that make any sense?
I'm trying to, I don't know if I'm overthinking, but I'm trying to like flip it in my head to that configuration.
Yeah, that's the hard way to do it.
Okay. Okay.
Well, there's lots of hard ways to do it. You see,
so the enantiomer of the enantiomer is the identical image.
Yeah.
Okay.
Yeah. It's like the enemy of what is it? The enemy of my enemy is my friend. Yeah, that's right. That's what I'm trying to get at. I'm trying to show you the easy ways of doing this. Good. The enantiomer enantiomer of a, I don't know how to, tell me how you said it really well. Say it again.
The enantiomer of the enantiomer
That's
is
good.
identical.
Yeah, that's good. The enantiomer of the enantiomer is identical. Now,
Okay.
does that make sense?
Yeah.
Is that something
That
you can
makes
live
sense.
with?
Mm-hmm.
Okay, so if you see that, you already know what's going on. So what that would mean is, it would mean that these over here, let's go with a little bit darker green, that these over here and these over here are going to be identical.
Yeah. Okay, that makes sense.
Now we could use that in naming, of course, because what happens is if we go ahead and name one of them, like let's say we name this one here, right? So this would be 1, this would be 2, this would be 3. Low priority is back. So we go around like this. This would be R. This is S. And this is R. And this is S. You see, you can do a lot of work. With these tricks, you can get a lot of mileage. Now, now the thing is that I kind of wanted to finish something here. It may not be the same one we had. It's close. All right. We're going to have to figure out whether this is R or S. The problem is that here, the low priority group is going to be in the plane. Now, I like to do this the quickest way. Some people have another way. I'll just show you the quickest way. I'm simply going to take the low priority group and switch it with the one going in. I'm taking the low priority group and I'm switching it with the group going in. So what that does, it keeps the methyl group where it is, and it puts the hydrogen here in the back, and then we have over here the chlorine. Now, when we switch two groups, what happens?
You have to, well, you're supposed to switch the other side too.
No,
right?
no. When we switch two groups, R and S switch.
Oh, yeah.
That was the rule. When we switch, then I'm going to tell you something funny. I kind of like to invent these rules to make people's lives easier. For me, that's what my job is.
Mm-hmm.
I taught someone all these rules, and he went to class, and the teacher was working out a series of R and S's, like 8 of them. And this was a pretty good student. He looked at all 8 without writing down, and he said, R, R, S, S, R, S, R. And the teacher laughed at him because he knew he couldn't do that. And he got them all right. And the teacher after class said, he went up to him and said, how did you do that? And he said, Rich taught me how to do it. And the teacher knew me. And he said, well, he's teaching you wrong. Don't do it that way. But it was an impressive thing. I mean, I'm not even sure I could do all 8 of them. They were complicated molecules, but he was using tricks.
Okay.
So but the point is that with these, you can do things more reliably without mistakes, and you can do them faster. So that's our trick here. So what happens is we know that R and S are going to switch. The teacher talked to me. We were friends.
3.
Yeah, and he said that you shouldn't teach him stuff like that. Okay, so
the priority to understand, so the priority originally was the chlorine, the methyl, and the ethyl. So it'd be R going
Okay,
that
well,
way.
let's only work over here. Let's only work over here. We don't need to look at this.
Okay. Okay.
Let's work over here. This is
So
1. This is 2. This is 3.
3.
So this is S.
Okay.
What's this?
But then because we switched it,
yes,
then it'd be R.
That's the whole point. You see, it's nice.
Okay.
Now, these are very brief, easy rules that are simpler than any other rules. This is as simple as you can get. So, so what I'm saying is that there are 3 possibilities when you have a molecule. What happens is you can have something like this. You can have something like this, assuming the hydrogen is a low priority, and you can have something like this. This, you just do it. Here, you're going to switch. And then for this one, you do what we did up over here. And when you do it, you're going to switch the hydrogen with the group going in so that you get something which is easy to work with. In other words, you get something with the low priority group going into the paper.
Okay.
Now that we know this, here's what we're going to do. We're going to put a chlorine here. We're going to put a chlorine there, a chlorine here, a chlorine here, and then we'll go ahead and put parachlorines over here and right over here. And just in case there's any question about this, I'm going to put methyls so that you see them here, but you don't actually have to put them. Okay, we got them here. And also, just because it will look nice, we'll fill in the hydrogens here in blue. And then we'll say that these are the chiral carbons here. Now, these Fischer projections have a particular property, and that is the horizontal bonds are coming out of the plane of the paper, like a big bow tie. And the vertical bonds are going in like this. So this is into the paper, and then this is out. Does that make any sense?
Okay.
You don't need to build a model. You could just say that's the way it is. Now, we're going to figure out the absolute configuration of this carbon here. First thing we're going to do is we're going to point out that this hydrogen is coming out. We know that because we just said it. If the hydrogen is coming out, we're going to switch the R and the S, right? Because that's what we said. If the hydrogen, if the lower priority group comes out, we switch the R and the S.
Okay.
Right? That was one of the rules. If the low priority goes in, we just do it. If the low priority comes out, we switch it. So we're going to switch it. So what happens is this will be 1, this will be 2, and this will be 3. So we're going to go around, and I like to turn it around. Okay, this is S.
1, 2, 3.
Is that?
So we'll use this trick for all of them then?
Well, we don't need to. We only need to use it for one of them.
So because the low priority, which is the hydrogen, is coming out, that means that we switch it in this situation.
Yes.
Okay.
Yes. In fact, we do it for all situations that we're working out this. If the lower priority group comes out, we're going to switch it.
Okay.
Now, I have a question for you here. Is this here the mirror image of this? Okay, it shouldn't take that long.
No, because it like it's on opposite sides.
Right, good. It's not the mirror image. If it was the mirror image, then this would be R. Because that's how it works. That's one of those rules. The mirror image of S is R. But it's not the mirror image. So it's S.
Okay, so the mirror image.
There's only two possibilities.
Okay. Okay.
This is not the mirror image of this. If it was, this would be R, because R is the mirror image of S. If it isn't R, it must be S. Same groups.
Okay.
That makes sense?
Yeah.
Okay. Now, let's take a look over here. Are these mirror images here? Just the bottom part.
Yes.
They are. This is S. What's this?
That would be R then.
Yes, that is going to be R. Oh, it appears we can do a lot with this. Is this the mirror image of this?
No, so it would be S.
If it was the mirror image, it would be S. Because S is the mirror image of
Oh,
R.
it's the same. It's the same. Okay, so it'd be R.
Yes. Now, I'm hoping that you're beginning to realize that this could be useful for you on the test. These are skills that will make it easier. I understand that not all of them are in the book. The teacher may not have taught you these, but you can use these to name things. Okay, we're going to name one of these, okay? But let's just continue. I'm going to just say this. What we have over here is identical to what we have over here. You see, these positions here are the same. Do you agree with that?
Yes. So
Good.
it'd be S.
You got the idea. This is S. Now, is the top and the bottom mirror images?
Yes. So it'd be the opposite, which would be R.
Perfect. That's absolutely wonderful.
And then I guess in addition to that one, would that one also be a meso compound?
Yes.
Since you fold it, it's the same?
Yes, because you fold it and it's the
Okay.
same, that's a meso compound. And then
Okay.
these are enantiomers.
Okay.
I recommend, I've given you several different rules, maybe 6, I think, rules here total, part of what we have here. I would maybe put them on a paper or a note card, these rules with examples, so you can practice these and stuff. Because the truth is that this is the bag of tricks right here. This will pretty much do it, what we've done. Now, let's go ahead and name this right over here, okay? So it's a meso compound, so what we're gonna do is we're going to do it alphabetically. R comes before S, and so we would number it to get the R first. So when we number this, what we'll do, let's use this color here. Yeah, 1, 2, 3, and 4. Because R comes before S, we give it like a 2R. 2R, comma, 3, S, comma, dash. And then it's going to be dichlorobutane. Does that make any sense?
Okay. Yeah, I see it.
Now, let's do this. Put a Cl here and a Cl here. And now, is this a meso compound?
Yes.
Okay, all meso compounds are going to have this, all of them. It doesn't have to be 2 and 3, but they're all going to have an R and an S. It doesn't matter which is which. All meso with 2 chiral carbons are RS. And that's logical because they have to have an internal mirror. So R and S are the internal mirrors. So we don't actually have to do it even. We don't have to figure out which is R and which is S because it's going to work no matter what we do. So what we would do here is we would say that this is going to be 2 R, and then this is comma 4 S, and then dichloro, and then this is a little messy, but pentane. That makes sense?
Yeah.
Okay. Now, if I were to draw something like this, I put 1 chlorine here, and I put another chlorine over here. That's not a meso compound. Do you agree?
Yeah, it's not. It would be.
So it's going to either be RR or SS because meso is RS. It's either going to be RR or SS. See, what you have is you have these as your possibilities. You have RS, that is going to be meso. You have RR, that's going to be an enantiomer. And you have SS over here. And that's going to be an enantiomer. Like that. So those are going to be our possibilities.
Okay.
Does that make sense?
Yeah, that makes sense.
Okay. So we don't have to do both chiral carbons, right? We just have to do one. Because we know that the answer is going to be here. Right? Yes, sir.
Yeah.
So I'm going to do this one because this one's easier because it's got the hydrogen going back like this.
So 1, 2, 3.
Right.
Should be R.
So this is 1.
Okay.
This is 2. And this over here is 3. And that's in the back. 1, 2, 3. That's R. And this is not the mirror image. So it's RR. Did that make sense?
Yeah.
Okay.
It'd be the same.
Right. So basically, as far as Fischer projections, we've done everything you need to know. As far as line drawings, I think we're pretty close to that. If they give you something ugly like this, dink, 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 like this, okay. Oh, I know. Yeah, let's do this one here. Okay, we'll do this one here. And then we'll put a chlorine here. And then we'll put a chlorine over here. Okay. You can't look at this unless you're kind of familiar with orgo and determine whether this is a meso compound. So one option is just to go ahead and figure out what this carbon is here. And the other one is to figure out what that carbon is there. Does that make sense?
Yeah.
But in this case, there's a trick. This is where you actually are doing something that they want you to do. You take this and you're going to rotate this. So we're going to rotate this around like this. Now, when you rotate something, I've got a trick here too. So this has got the hydrogen in the back. And then what's going to happen is this over here is going to have a hydrogen in the front. And the reason I know that, I could actually put it on the other side to make it look better, is though that rule I told you, there's the hydrogen there. I told you that you have two lines like this, and then you have this, and then you have that over there. Okay. So if I rotate one of these lines here by 180 degrees, what's going to happen is the wedge and the dash are going to switch. So there's another rule to make your life easy. So if you rotate this 180, the wedge and the dash will switch. You can do it on models, but you don't have to do it. You can just know the rule. So you have a chlorine here, you have a hydrogen right over there, and now this line is here. See right here, that's there. And then these two are switching. So what that means is the hydrogen is here and the chlorine is there. So that's, yeah.
Okay.
Is this meso?
Yes, because it's a mirror image.
Yes. What's the name of it?
It would be 1, 2, 3. So it'd be 2R,
Yes.
or RR. Yeah, 2R, 3R, 1, 2, 3, 4, dichloral butane.
Yes. That's right. That's right. So those are the tricks for naming, and what I'd recommend you do is you use them and do as many practice problems as you can.
Wait a minute.
Okay.
Let's see, 2R, 3R. What about the trick that we just had that you said the meso was R and S?
Oh, yeah. You
Does that
told me
apply
this
here?
was R and R, and I stopped listening to you. Absolutely. It's definitely an S here. I was euphoric that you got it right, and I wasn't paying attention. So I apologize for that. Yeah, it's 2R, 3S.
2R, 3S. Okay.
Because that's
I just have to remember the trick.
That's the trick, right?
Because when you rotate it there, that's why I said 2R and 3R, because it would just be going the same direction.
Yeah. Well,
but I realize you have to name it based on the original, right?
Well, the thing is that these molecules are the same molecule. They're just different conformations. So technically, you can name it on any of them because they all have the same name. Does that make sense? That they all have the same name? Yeah.
Yeah.